So integration using substitution. It is a 3-unit topic, but that obviously doesn't exclude you from using the technique in extension 2, of course. In fact, you might have to. The main difference, I guess, between the questions in extension 2 and extension 1, extension 1 they will give you the substitution to use, whereas in extension 2 they may not, and then you just make your own mind up how you want to do it. Now, personally, I would prefer if they didn't give it to me, but we'll see why when we look at a few examples. Basically what we're trying to do is turn our integral into a standard integral, so something we know how to integrate. Prior to 2016, you used to be given a set of standard integrals. That was all there was. There was no reference sheet. And these were the integrals that came in very handy. They said, oh, well, x to the power of n. Oh, add 1 to the power over the power. 1 on x, log x. E to the ax, oh, it's 1 on a, e to the ax. Integral of cos is sine. Integral of sine is cos. Sec squared, oh, that's tan. Sec x, tan x, sec x, that was handy for conics, I suppose. There's the one that goes to inverse tan. And, well, they say inverse sine, but as we now know, it could be minus the inverse cos. And then with these other beautiful ones, which were mainly for extension 2 students, 1 on the square root of x squared minus a squared, and 1 on the square root of x squared plus a squared. So that's what we used to get. What we now get a wonderful reference sheet which has all sorts of formulas in there. Area of a triangle, it's handy. Things like that. But the integrals that are in there, and they actually break the reference sheet up into mathematics and extension 1. And they don't have extension 2. So instead of just doing the x to the n, they actually did go that useful theorem idea of the linear function. If it's a linear function to the power of n, you still add 1 to the power over the power, but we multiply by the coefficient of x on the bottom. And the exponential now, instead of just having ax, they make it a whole linear function, ax plus b. For log, rather than just having 1 on x, they go the whole, derivative on function. And remember, technically it's the log of the absolute value of function x. Sine, again, they go the whole linear function. Cosine, and of course there's sec squared. That's pretty much it for 2. Then on the extension 1 sheet, they also have the inverse trig ones. So there's inverse sine and inverse tan. Notice they don't have the sec x tan x, which is useful for conics. They don't have those other 2 that I said, oh, that'll come in handy for extension 2. We're just expected to do them. Then there are these, also not on the reference sheet, which I shall call the non-standard integrals, which, well, they are standard integrals, they just choose not to give them to you. Not listed, but if you memorise these, it'll save you some time, because they occur a lot. Du on root u, well, that's 2 root u. That's just going to save you time, because if you see du on root u, well, what you got to do? Oh, well, that's u to the minus a half, add 1 to the power over the power. Oh, let's put it back in third form. It's just easy to know. Hey, that'll always end up being 2 root u. Similarly, the du on u squared happens a lot as well. So, okay, that's minus 1 on u. Integral of log x. Again, not one of the standard ones, but it's x log x minus x. You'll see the integral of log x a lot. So again, that one will save you some time if you just remember it's x log x minus x. Integral of tan. We talked about that when we were back in trig. Remember, the integral of tan is the log of sec x, or alternatively you could say minus the log of cos x. But then there's this idea. If you have to integrate a complementary trig ratio, the answer will be always negative the complement of the answer. Well, what do I mean by that? Integral of cot x then. Well, I know tan equals the log of sec. So it's complementary, so the answer should be minus the complement of the answer. Right? So cot's the complement of tan, so the answer is going to be minus, and the complement of sec is cosec, so I get minus the log of the cosec of x. So you change the ratio to its complement, you whack a negative out the front. So that's handy to know. And yeah, I brought the minus in, so that becomes the log of sine. Okay, so let's look at this idea of integration by substitution. We want to convert to a standard integral. X root x squared plus 4. Well, what's causing me the problem? I guess that's the first thing you look for. But remember I said extension 1, they're going to tell you what to use. But it's always more fun to work it out first for yourself to see if you can. And usually you see something with a square root. The square root's what's causing me the problem there. So I'm going to make that the function. So u is going to be x squared plus 4. That's what's causing me the problem. If it was just root x or root x squared, I don't have a problem. But it's x squared plus 4. I've got a problem. So if u is x squared plus 4, there's u. Du then is 2x dx. You could think of it as saying, well, I've differentiated du dx is 2x and I've multiplied both sides by dx, if you like. And, well, hang on, there's x dx, so I've got a half du. I have to eliminate every variable. I can't have a mixture of x and u's. So everything's got to be changed. So I end up with a half of u to the half. Oh, well, add 1 to the power over the power. 2/3 u to the 3 on 2. A third u 3 on 2. That's not the final answer though, because the final answer has got to be in terms of x. So sub back in for u, and we get a third x squared plus 4 to the power of 3 on 2. Well, that would be the mere mortal answer, of course. Ah, that's so much better, isn't it? 1/3 x squared plus 4 root x squared plus 4. Plus, of course, a constant. Okay. I could have done it another way, though. So it all comes down to what substitution they give me. I might have decided that, you know what? I might try a trig substitution. When you see like a square root of an x squared plus or an x squared minus or something like that, then maybe turn it into a trig integral. Because the trig identity can turn two terms into one. So if I make this one 2 tan theta, x is 2 tan theta, dx then, differentiating that, will be 2 sec squared theta. So let's substitute in. Notice, by the way, I've made x the subject rather than theta the subject for this. It looks a lot worse, but it's not. Okay, the x becomes 2 tan theta. The square root of x squared plus 4 becomes the square root of 4 tan squared plus 4. Well, I know 1 plus tan squared is sec squared. So I now have 4 sec squared. The square root of 4 sec squared, 2 sec. Multiply that by the 2 sec squared, and I now, all up, have 8 tan theta sec cubed theta. Well, I could rewrite that as sine theta on cos to the power of 4. Now I'm going to do another substitution. Okay, well, let's u equal cos theta. Du equals minus sine theta to theta. So now it becomes minus 8 du on u to the power of 4. Well, add 1 to the power over the power, I get minus 8 times minus a third u to the minus 3. 8/3 sec cubed theta. But of course we want it back in terms of x. Well, I'll just draw myself a little triangle here, because I know that if I rearrange x equals 2 tan theta, I'll get tan theta is x on 2. So opposite over adjacent, x on 2. Hypotenuse becomes square root of x squared plus 4. I can now read off that triangle what sec cubed is, or sec is anyway. So it'll be the square root of x squared plus 4 cubed, which is x squared plus 4 square root of x squared plus 4. Now, let me just point something out here. If you are making a choice as to what to use for the substitution, and you choose x equals 2 tan theta for this one, you're mad. Right? That's just to show you different substitutions can work. That was a heck of a lot more work than the other way. Okay? So there are different substitutions you could use. Now, if they tell me which one to use, and that's why I think sometimes extension 1 questions I don't like as much as extension 2, because when they force me to use a certain substitution, sometimes you look at the substitution and you go, are you kidding me? Why would I use this? That's crazy. Always keep an eye out for this idea, by the way, because that essentially is what we had here. I wouldn't even do a substitution for this question, because look at it. I've got derivative times the function. I could have made that 2x outside of the square root of x squared plus 4. I've got derivative times function, add 1 to the power over the power, got the answer. So if it's one where you don't have to use a substitution, remember all those ideas that can save you time. All right, let's look at this one. Whenever you see a fraction with polynomials and you notice that the order of the top is one less than the order of the bottom, fair chance you got a log. Because when you differentiate a polynomial, the power goes down by 1. So you probably can create derivative on function, which is what I would normally do with this until they say, use the substitution, u equals 4x squared plus 8x minus 7. It comes out quite nicely this way anyway, though. Du would become 8x plus 8. Oh, I've got x plus 1. So I could change that to 1/8 of du on u. Now it's a standard integral. So it's 1/8 log u, substitute the u back in, and I've got the answer. Got the answer. Dx on x log x all cubed. Now, I hope I'm going to use the sensible substitution. What's causing me the problem here? It's the log function that's causing me the problem. So, yep, good, that's the substitution we're going to do. U equals log x, so du is dx on x. We've got the dx on x there, that's good. So it's du on u cubed. Add 1 to the power over the power. We've got to substitute back in for u. We get minus 1 on 2 log x squared. Okay. X over the square root of 1 minus x. Okay, before I see what substitution I'm given, what would I do with that? I suppose logic kind of says maybe make it 1 minus x. That's what's in the square root sign. But no. They tell me to do something different. X equals 1 minus u squared. So in fact, we're not going to substitute for the 1 minus x. We're going to substitute for the whole of the square root of 1 minus x. So they told me x is 1 minus u squared. Rearranging that, I can see that, u is basically the square root of 1 minus x. Dx then is minus 2u du. When they give me a substitution where x is the subject, it's kind of nicer, because I can just sub straight in, because I can work out dx and go, bang, there it is. So substitution, u equals function x instead of x equals function u. There's some domain issues that can crop up from time to time when you're dealing with functions, of course. So that's why sometimes they will say, yeah, use x equals 1 minus u squared, instead of saying use u equals the square root of 1 minus x. Because square root of 1 minus x has problems on the domain. Okay, let's play around with it. Integral of 1 minus u squared over u times minus 2u du. Oh, u's cancel. Oh, it's just a simple polynomial. U squared minus 1. Add 1 to the power over the power. Sub back in for the u. Mere mortal answer. So much nicer. 2/3 1 minus x root. 1 minus x minus 2 lots of root. 1 minus x. Plus, of course, a constant. U equals sine x. So du is cos x dx. And you think, well, that's not that big a deal, except for one thing. Those limits of pi and 2 and pi and 3, they refer to x. So I've also got to change them as well now. So when x is pi on 3, u will be the sine of pi on 3, which is root 3 on 2. When x is pi on 2, u will be the sine of pi on 2, which is 1. So my integral now goes root 3 on 2 to 1, u to the power of 5 du. Add 1 to the power over the power. Now, of course, the advantage of a definite integral, because I've changed those limits, I don't have to substitute back in for u now. Because my limits are in terms of u, I can just sub in and get our final answer of 37 on 384. What are they going to make me do? u equals 25 minus x squared. So the u is minus 2x dx. We're going to change the limits. X is 3, u is 16. When x is 4, u becomes 9. So my integral now is, well, the u was x dx, so we got minus a half of that. And the u on root u, which by the way is 2 root u. So it crops up a lot because you're doing substitutions. So I could have just gone bang, 2 root u. But anyway, let's go the long way here. So u to the negative a half, add 1 to the power over the power. And, well, the 2 multiplies with the half, so I just get u to the half, square root of 16 minus square root of 9, which is 1. They're going to make me do it by saying x is 5 sine u. So in other words, u is the inverse sine of x on 5 is our substitution. So dx is 5 cos u du. I'm going to have to change my limits. When x is 0, u is inverse sine 0, u is 0. X is 5, we get u as pi on 2. Substitute in, you are so mean. Okay, I get the square root of 25 minus 25 sine squared. But hang on, 25 minus 25 sine squared is 25 cos squared. The square root of 25 cos squared is 5 cos u. 5 cos u times 5 cos u is 25 cos squared. Now we have to integrate cos squared. Oh, hang on a sec. Cos squared, that's a half of 1 plus cos 2u. Now we can integrate. We get u plus a half sine 2u. Substitute in the pi on 2. Substitute in the 0. We get 25 pi on 4, eventually. Or, had they not given me the substitution, and I recognise that was a semicircle, but 0 to 5 would be a quarter of the circle, I could have just gone, oh, it's a quarter pi r squared. Again, you recognise the shape, save yourself some time. Unfortunately, I could not, to answer your question, I could not have done that for this question if they had said using this substitution. Oh, by the way, don't forget about manipulating algebra as well. That can help out. Look at this question. Integral of x cubed square root of 4 minus x squared. I'm going to rewrite that as you would. Instead of x cubed, I'm going to write it as minus x, 4 minus x squared plus 4x. That's x cubed. But look what happens. I can split it into two things, but both of them now are in the form derivative times function. Derivative times function. So sometimes you can play around with the algebra to make life a lot easier. And thank goodness I didn't get via a substitution. I can just go add 1 to the power over the power on this one. And woohoo, look at that. What an answer, hey? Are we having fun or what? Okay, so here we go. 6C and D. So they're the extension 1 questions, so they'll probably give you the substitution. Patel in our Cambridge obviously is extension 2, and substitution is not necessarily given to you. You might look at the integral that they give you, decide, hey, I don't need to use a substitution for this, I'll do it this way.